All right, so let's do an example about the force response, but undamped. So in this case, again, we're going to have those two masses. K2. K1. K3. Right. M1, M2. Okay. So now this one here is going to be subjected to a force F1t equal to F1 cosine capital omega t. So since we already mentioned it, this will be the relative coordinate system. So we have x1 that start from the CG of the mass M1, x2 that start from the CG of mass M2. Okay. So for this problem, we're gonna have that K1 equal K2 equal K3. Let's say will be equal to K. Okay. I'm gonna say that we're gonna take the simplest case, M1 equal M2 equal to M. Okay, so I'm not going to recopy everything, but if you go back to the notes, we know that the equation of motion for this type of system with this data will be what? So we'll have here M1, which will be M plus, this should be K1 plus K2, so it should be 2K. This should be minus K2 minus K, and then this one should be K2 plus K3, which is everything is the same, should be 2K. X1, X2, and this should be equal to the force, which in this case, in this example, is only one applied to the mass M1. So it should be F1 cosine capital omega t, and this would be 0. Okay, so like always, what is the procedure? I didn't do the Seaborn diagram because we already have it, but you can do it very quick and then just do the equation of motion. Then next thing is to solve this equation. Okay, so if you remember from the 1 degree of freedom, what was the normal procedure when solving this problem? We first solved for the homogeneous case and then for the particular, no? Okay, so here we do exactly the same thing. So solving first the free vibration problem, which means basically F1 equal to 0. Why do we first solve the free vibration problem? Because if we want to solve the free vibration problem, we need to have here the natural frequencies, no? Okay. All right, so that's basically the reason. So that means I want to start going a bit faster, that we need to solve the problem M00M x dot dot 1, x dot dot 2 plus 2k minus k to k x1, x2 equal to 0. Okay, so now how do we solve? We assume the solution. X of sub j equal to capital X sub j e I, but this time would not be capital omega, would be lambda t, which is the natural frequency, where in this case, j will be equal to what? 1, 2, no? Okay, for the first one and then for the second one. And substituting into free equation of motion. So basically into this equation here, it's always the same thing. We can factor here by E I lambda t. After you take twice the derivative of this, you get I squared, which is minus 1. So we get again minus m lambda squared plus 2k minus k. And then this one would be minus m lambda squared plus 2k minus k. One x2 equal to 0. Okay, so now what is the next step? This equation is satisfied if and only if, since this is never 0, no, when x1, x2 are equal to 0 will be the trivial solution, or when the determinant of this is equal to 0. All right, always the same process. So previous equation is satisfied if and only if, that's the way I write it, and I with two different f's, okay? One, you can write if and only if. So we have x1 equal to x2 equal to 0, which gives the trivial solution. Or when this term over here is 0, which mathematically this is represented by saying that the determinant of minus m lambda square plus 2k minus k minus k minus m lambda square plus 2k basically is equal to 0. All right, so if we solve for the determinant, what are we going to get? So we should get minus m lambda squared plus 2k times minus m lambda squared plus 2k. So I can just put this one square minus these two that are negative, so we'll give positive minus k squared equal to 0. All right, so let's do the algebra over here. So this should give you what? M squared lambda to the 4 plus 4 k squared minus 4 mk lambda squared minus k squared equal to 0. So we're going to get here the equation m squared lambda to the 4th minus 4 mk lambda squared plus 3k squared equal to 0. So this equation here is known as the characteristic equation. Okay, so now what do we need to do? We need to solve this quadratic equation. Really, it's called B quadratic because here what will be our variable? Our variable will be lambda squared, no? Okay, so solving B quadratic equation for lambda square. Okay. Okay, so if you want to do this symbolically, you can use maple. I just type the equation, but remember this should be to the 4th. But so this is basically lambda squared. So we can say that the first root would be, if we start from smaller to bigger, but it doesn't matter. We're gonna have that lambda 1 squared is omega 1 squared. Remember the natural frequency, so this should be k over m. And the second natural frequency, lambda 2 squared equal to omega 2 squared, is 3k over m. Okay, so if we were only solving, if in this point you had no force, what should be the next step? Solve for the eigenvalues, eigenvectors for each one of these ones. That should give you the type of motion that you could have, no? So what are the two type of motions you can have over here? Either they move together or they're going to move away from each other, no? Okay? But again, in this case, since there is something forcing the motion, you're not going to have, you don't have to solve for the eigenvectors. Okay? So we did this first part, but this is important, you will see why. Okay? I mean, if you want, I can show you now. That way, you don't have to wait. is that if you remember when we only had 1 degree of freedom, we had 1 resonance frequency. Okay, when there is damping, this is closed. When there is no damping, the amplitude goes to infinity. All right. Now that you have 2 degrees of freedom, 2 masses, what's going to happen? You're going to have 2 different resonance frequencies. Okay. So this value over here should be the K over M. This one over here should be the 3K over M. No. Okay. So when you do the plot, so then what happens when you do your design? The last thing the last thing you want to happen is your force frequency to be equal to one of those 2 natural frequencies. Yeah? Okay? So I explain it now, and that way we go now. So now, after we have the natural frequency, we need to go and solve for the force frequency. All right, so now solve for undamped forced vibration problem. So this is what we did at the end of last class. But again, it's the same procedure. The only difference is that this time, instead of assuming the solution in function of the natural frequency or lambda, we're going to assume it in function of the force frequency. Okay? So in this case, the equation of motion is what? M 0, 0, M, same as before, x1, x2 plus 2k minus k minus k 2k, x1, x2 equal to f1 cosine capital omega t 0. Okay, so what is the next step? Assume solution x of j equal capital X of j e, but this time, what should be the answer here? Capital I omega t. All right, let me double check. This is what we used last time. I'm pretty sure it's what we did. Yep. Okay, and if you want, then it's substitute into above equation, which is this one. And then if you want, this is not that important, but we have done it many times already. F1 cosine capital omega t, this will be equal to what? To the real part of this one, no? Okay, so why is that important? Why is that important? This is what we did the other day. This is the lambda. Why is that important? Because now, when you come to this step, you can cancel this one, no? Okay, so I'm not going to redo it over here, but this is basically what we are doing. And we did that all this stuff the other day, and at the end, we find out that the expression for x and 2 were equal to these 2 expressions. All right? All right. Okay, so the solution is so we had x1 here. I'm just going to write the two expressions. We had x1 equal to f1 z22. I'm going to forget about the I omega. Okay, I'm going to be a bit faster, minus f2 z12 divided by z11 z22 minus z12 squared, and x2 equal to minus f1 z12 plus f2 z11 divided by z11 z22 minus z12 squared. Okay, where here we have z rs, or yeah, that was equal to what? Let's see if I can go back to the notes. Yeah, I remember what it is, but so this is the z, here it is, should be up, is the, so in our case would be the minus rs capital omega, there is no damping, plus rs. Okay, so let's do it slowly since we have time. So in our program, what do we have? There's only force F1, no? There's no F2, so that will be 0. So then we have F1 equal to F1, basically. Not much to say. Then we're going to have, since these are the same values, since these are the same, this will be the z's, no? Okay. You can say that z11, z22. So z11 equals z22 is equal to that expression there, minus m. But this time we need to change the lambda by the capital omega. And that should be minus, so now plus 2k. I'm just looking to this expression here. Plus 2k. And z12 equals z21. That should be equal to minus k. All right. So we just need to substitute into these equations. So substituting into x1 and x2. What we're gonna have? So we have x1. So f1 remains f1. Now m2 z22 is this expression here. So this will give us minus m capital omega plus 2k. F2 is 0. Divided by Z11, Z22 will be minus M capital omega square plus 2K square minus K square. Okay, so now you can trust me, or you can do the algebra if you want, but you can rewrite here so the top remains the same, but let's just write it, so it will be minus M lambda square plus 2K. But after you expand here the square and you simplify by this one, okay, you end up with the quadratic equation, all right, where the two roots would be, so you basically can write the denominator as minus lambda square plus 3K times minus lambda square plus K. Yeah, I mean, it's just algebra. You need to develop this and then solve for the two roots of the quadratic, no? Now you can rewrite under this form. So this should be the two roots. So actually you see that here the two roots are the same as before. 3K over M for this one and K over M for this one, no? Okay, that would be equal to the natural frequencies. Okay, so we're gonna say now, using notation that omega 1 squared is K over M and omega 2 squared equal to 3K over M, which basically will be the two roots over here. We can rewrite X1 as being equal to F1M. So a factor of the M outside, okay, minus lambda squared plus 2 K over M divided by M squared, factors of minus lambda squared plus K over M times minus lambda squared plus K over M. All right, so we can write this as F1 over M times 2 omega 1 squared, which would be this one here. The K over M is omega squared minus capital omega. And the bottom could be, this would be omega 2 square minus capital omega times omega 1 square minus, oops, I forgot the square over here, square minus capital omega square. Here this is a square, okay? But it's very small, but it's a square. Okay, so now if I factor out the omega 1 square, what are you gonna have for this one? You're gonna have okay, so let's do the steps. So let's factor out first by the. So we factor out this one by the omega 1 square. What are you gonna get? 2 minus capital omega divided by omega 1, everything squared. Okay? And now the lower part is probably going to be much longer. We're going to factor as well by omega 1 square. So what are you going to get? Let me do brackets here, might be a little bit cleaner. You're going to get, so let's switch the other. So this will be omega 2 square. So you're going to get omega 2 over omega 1 square. This is this term, no? Factoring out. Minus this one, that would be minus capital omega over omega 1 square. Now the second one will be so what is K over M? What is K over M? K over M is omega 1 square, no? So if we factor by omega squared, it should be 1, no? Yeah? So this term should give you at the end 1 minus the capital omega divided by omega 1 square and this. So hold on 1 second here. That become a bit. So what's going to happen now is that you can cancel this one with 2 of these ones. All right. So you're left with a square. And then what do you know? Omega 1 square is equal to K over M. So if this is equal to K over M, that means that the M is going to cancel out. And we're left with a K. Okay. Again, this is just algebra. It's not that important, but since we don't really use the textbook, I want to give it to you. So at the end here, we're going to get that X1 will be equal to F1 over K times 2 minus capital omega 1 square. They use the brackets, looks a bit cleaner. And then at the bottom, we're going to get the omega 2 divided by omega 1 square minus capital omega divided by omega 1 square times 1 minus capital omega 1 square. I mean, again, it's not important that you know how to do division, but at least that you follow us, we do it together, no? Okay. So, as you can imagine, if you want, you can practice, but we could do something similar for X2, no? All right, but we're not gonna go through the details. So similarly, you will get that x2 will be equal to f1 over k of basically the same thing as before over here would be omega 2 omega 1 square minus capital omega divided by omega 1 square times 1 minus capital omega 1 square. Okay, so now this is really the important part of these derivations is you could do this with Maple very quick, no? Okay, but so the notes. So now the important part is that don't get confused over here with let's see. So basically here you see this is x1 k divided by f1, but you agree that k over f1 is a constant, no? So really here what we're saying is what is the response of x1, and here basically the same thing, k over f1 is a constant, so really we're looking at x2. The reason we do this is because in our solution we have here f1 over k, no? Yeah, so what I want to plot is really this, which is in function. So really what I want to, so this is 1, this is f1 over k. What I want to plot really is this part over here, which gives the change with the frequency. Okay, so over here, I hope it's, see if I can zoom in a bit more. Again, this is the important part, is to understand what's happening here physically. So I put it here on this figure, but what's happening here? This is the first resonance frequency, no? It should be omega 1 as I put over here. So it should be here the value for omega 1. But this is normalized because when capital omega, the first frequency is equal to omega 1, you will have 1, no? Yeah? Okay. And now this will be omega 2. All right? So the important part over here is what? So like I said before, is that you certainly don't want to have your omega right here or right here. Okay? So let's see what are the two comments that I put. And so this is the response for x1, and this is the response for x2. Okay? So you see both are here, but then this one intersect this one and this go this shape. I don't know the reason of that. Okay, so let's see what I put over here. It can be observed from the above figure, I don't know which one, that the amplitude x1 and x2 becomes infinite at the two natural frequencies, which is what we just commented, which correspond to the two resonance frequencies. At all the other values of capital omega, the amplitude of vibration are finite. So basically, that is true. Here it goes to infinity, infinity. But if you stay in this area, in this range or this range, the amplitude x1 is finite, and here the same thing, no? Okay, actually here you see that here is pretty small and it keeps increasing, but actually here we'll go from large to slowly going to 0, no? I don't know if it will go to 0 or it will stabilize over here. I think we'll just remain constant over here. For X2, what do you see? It starts small, it's going to grow up. Then in the middle, it looks like decreases, stable, and then increases again for the second resonant frequency. The same thing here. But here basically goes from negative to positive, no? Okay? And here just remain negative, but it remains over there. So what is the other comment that I put? It can also be I guess it can also be noted that, and here from the above figures, that there is a particular value of the frequency omega at which the vibration of the first mass, M1 equal M2, to which the force F2 is applied, is reduced to 0. Okay. All right. So what happened here to the motion of X1? Here at this point is going to be 0, no? Which is what I just put over here, to which the force applied F1 is applied, reduced to 0. These characteristics forms the basic of the dynamic vibration absorber. So basic is probably something we're going to do next. So now what can you do in your design? Maybe you can do your design, you can select the springs or the masses, no? So that when you have the natural frequency, that can be your engine, okay, or your machine, that you will have the minimum deformation X1, no? By playing with the values of the mass K and the mass M, because omega 1 is equal to what? Square root of K over M. All right? So one way, if you want to do a passive, I'm talking over here. So one way to do a passive absorber would be what? To play with the value of K over M to try your system to operate over here. If you operate over here, what are you going to have? X1 equal to 0, and here X2 will be what? We actually will not be the minimum, but will be pretty reduced, no? Okay? Does that make sense? All right, so